Hello everybody. Today we're going to take our first look at capacitors. I'm Michelle Maharviz.
And I'm Vivek Subramanian. Let's get started. Okay, so to begin, let's recognize what a capacitor is. A capacitor consists of, in a simple form, two plates that are separated by some sort of insulating region between them. Now, the idea in these is that you can use these plates to store energy in the form of an electric field. Think about what that means. I can take this device, and if I were to somehow add positive charge on one side, negative charge will be induced on the other. If I were then to disconnect whatever I use to charge it up, it should, in an ideal world, hold its charge. And it holds that charge, and since it has a positive charge on one side and a negative on the other, there'll be an electric field that results. So in other words, we can think of a capacitor as an element that stores energy in the form of an electric field, and we call it a passive element because it's such a simple device in this sense. It doesn't do any active function like a transistor would. Now, this also tells you something kind of interesting about this capacitor. If you think about this capacitor, what I did was to charge it up, I put positive charge in on one plate that induced negative charge in the other. So when I'm putting positive charge on one plate, in other words, current is flowing in, and my other plate is inducing negative charge, I effectively am allowing current to flow through the capacitor while the voltage builds up. At some point, the voltage will build up high enough that, let's say, I'm no longer able to put current in, and it'll sort of max out for the given voltage and current that I've applied. So for these capacitors, it turns out there's some fundamental relationships that come out of that behavior. First, the current through a capacitor turns out to be proportional to the rate of change of voltage. If I were to ramp up the voltage, for example, I would see a current flowing through the capacitor. The proportionality constant is capacitance C. And that capacitance C is the magnitude associated with the capacitor. We'll talk about the units of capacitance shortly. Correspondingly, because I'm building up charge on this capacitor, we use a term Q to denote the charge in the capacitor, and the following relationship evolves. Q, the charge in a capacitor, is equal to C, the capacitance of that capacitor, times the voltage present across the plates. You can put these together, therefore, to establish an overall relationship. And the relationship is taken from this differential equation, where we can basically solve the differential equation to find the voltage. In other words, if we have a capacitor and we have some current flowing into the capacitor as a function of time, starting at time t0 and going through time t, the voltage that builds up on the capacitor is going to be 1 over c times the integral from t0 to t of the current with respect to time, plus the initial voltage that was present on that capacitor starting at time 0.
All right, let me try to wrap my head around this. So, first thing you're telling me is that as current is being run through this element, what it's doing is effectively generating charge separation, or say positive charge on one plate and negative charge on the other, which of course sets up an electric field. But what you're saying is that if I were to, for example, to hold that current constant, I'm forcing this thing to always have, say, an amp running through it, then that value, say 1 amp, is equal to some proportionality constant, and that times the derivative of the voltage. So if then I want to solve for the voltage, I'm essentially putting the C, putting it out over here, so it's I over C, which is what you get here, and integrating to get the voltage. So for a steady current, the voltage is going to go up.
Right. The way to think about it is the following. If I've got a fixed current that I'm forcing into the system, what am I doing conceptually? I'm keeping on adding, let's say I'm using positive charge, I'm keeping on building up positive charge on one plate, which is causing negative charge to build up on the other plate. As I keep building up charge on the two plates, what's happening to the voltage?
Well, it's going up.
It keeps going up. So what I'm doing conceptually is if I force this constant current into the system, over time, the voltage will keep rising. Okay. And that's really what this equation describes.
I get it. And then the role of this equation is to say, we said in English that a certain current gives rise to charge, on both plates, and that charge gives rise to a voltage change. This current is telling us how much charge and how much voltage and how they're related. In other words, for a certain amount of voltage, you need so much charge on each of the plates, and that is given to you by C. So my guess is that C is going to have something to do with the geometry and the materials in here, such that you relate these two variables.
That's right, and we'll come to that in a little while.
All right.
So this is conceptually sometimes a little complicated to think about. It's easier to think about it qualitatively than to get the quantitative aspects, I personally find.
Mm-hmm.
It's fairly easy to understand that if I were to flow a current, it would build up charge, which will cause a voltage. To get the underlying relationships takes a little bit of thinking. But remember, that's what this equation basically codifies for us. In other words, I keep flowing the current, that causes charge to build up, which causes the voltage to rise. So between this equation here and this equation here, it establishes that dependency.
Okay.
All right. Now, if we think about that, let's ignore the fact that we can charge up the capacitor. Let's say I've charged it up to a particular voltage.
Mm-hmm.
At that point, once it's charged up to a particular voltage, do you think current flows through that, Michel?
No, I guess once it's held constant at some voltage. In other words, I disconnect the two nodes such that current can't flow, and it's holding its charge. It really kind of looks like an open circuit, right? There's no conductor between the two plates.
That's right, because think about it. What have I got here? I've got two plates which are conductive, but they're separated by an insulator. So as far as DC is concerned, once you ignore that initial charging step, a capacitor looks like an open circuit.
Okay, that makes sense to me.
Now, the other way to think about a capacitor that I find really useful is a capacitor really doesn't allow you to abruptly change voltage, because the only way for the capacitor to change voltage is to build up charge.
Mm-hmm.
And that charge buildup happens through this sort of steady current flow. So in other words, a capacitor works to fight against changes in voltage. You cannot take a capacitor and instantaneously change its voltage by some abrupt value for a finite amount of current, because the current has to follow this integral relationship such that the voltage can build up.
That's right, because if you had an instantaneous change in voltage, you essentially have a place where there's like a step discontinuity in the voltage trace, and that's going to require essentially an infinite amount of current.
Exactly.
And
Remember,
there's no such thing as an infinite amount.
Right. An instantaneous change in voltage means dV dt goes to infinity. If dV dt goes to infinity, the capacitor would require an infinite current,
right,
which doesn't happen.
Right.
So therefore, what we can say about the capacitor is a voltage change in a capacitor must be continuous. So a capacitor works to prevent abrupt changes in voltage. Now, Michel, you mentioned earlier that you think that this capacitance has to do something with the geometry of the capacitor. That's absolutely true. The classic example that we use for a capacitor is the so-called parallel plate capacitor. And a parallel plate capacitor consists of two plates of given surface areas laid on top of each other with a gap insulator between them. That insulator has some dielectric constant associated with it, epsilon. Then for that device, the capacitance is equal to epsilon, the dielectric constant of the insulator, times A, the intersecting cross-sectional area or the superposed cross-sectional area of the plates, divided by D, which is the gap between the two plates.
Okay, let me try to do some intuitive reasoning about this. So if my area is bigger, so if I keep the gap the same, keep the insulator the same, and I just say double the area, my capacitance will go up. And if my capacitance goes up here, the amount of charge that I am putting on this plate, plus Q and minus Q, for the same voltage goes as that change. So if I double the area, the capacitance doubles and the amount of charge doubles. And that makes sense, right? Because pretend I take another one of these plates and I glue it onto the end here, and the same with the bottom, I'm going to get twice as many of these little plus signs over here, right? The same amount over here, and the same amount of these negative signs over here, and the voltage will stay the same. So that's a kind of a quick sort of intuitive notion of how this geometry gives rise to the QV relationship.
Right. I mean, put it very simply, the more area you have, the more space to store charge, right?
That's right, exactly.
So that's the basic
For
idea.
the same voltage.
Yeah. Now, the units of capacitance are farads. Now, farad turns out to be a huge value. So in real capacitors that we deal with, we're typically not dealing with things in farads. We're living in the world of picofarads to nanofarads to microfarads. In some applications, you'll get into the low millifarad range. But that's typically where we are. We rarely deal, I'm not aware of any system that we deal with in any real-world application that we are actually counting on individual capacitors in farads.
Yeah, I think power plants have some fairly large capacitors.
Correct. That's the exception to the rule for very large systems, and a farad capacitor is an enormous thing.
Enormous.
Okay.
In fact, when you guys see the term supercapacitor that's thrown around these days because it's used in, for example, electric vehicles and so on, these things, are even those tend to be below a farad. I mean, a farad is a very large number. Well, let's keep going. Now, what I wanted to do is talk a little bit about why we get that relationship. And this slide is really for those of you that like to have a more rounded out intuition about how this works. We'll do this pretty quickly. So think about capacitor, the parallel plate capacitor we just talked about in the slide before, and it's connected to some source. And here's the notation for this element. Now, remember that like charges repel from your physics. So if I have a plus charge, it's going to be repelled from another plus charge. They don't like to be brought together. There's a force between them that repels them, okay? And the opposite is true between a positive and negative charge. They'll be attracted, okay? So if that's the case, we have to perform work. We have to do work to cram positive charges closer and closer to each other. Right? So if I have a plate and I have positive charges accumulating on it, to add another positive charge to it forces us to do work against the field created by that force between the positive charges, because they repel each other. It's a fairly straightforward idea, I think.
Okay, I think I get it. So what you're saying is once I've got one charge on there, the second charge is harder to put in, and the third charge is harder still, and so on.
That's right. And by definition, the potential across a capacitor is the amount of work required to move a unit of charge onto the capacitor plates. If you remember our original definition of voltage, this fits perfectly into that idea. So the voltage is really telling us, this potential is how much work I have to do per unit charge, right? So this is the work that has to be done by whatever source is generating this I, right? Whatever's running this current that's pushing charge onto the plates, all right? And so as you push more charge onto the capacitor with this fixed current, more and more charge of the same kind gets crammed onto this plate and charge gets induced on this plate. And so the voltage increase is going to keep going. The voltage is going to keep increasing. It's going to keep going up because because the voltage represents the amount of work per unit charge needed to push a charge onto the plate, it's getting harder and harder and harder. It's exactly what Vivek just said. And so that's why we expect to see the relationship in the previous slide, that the voltage is going to be proportional to how much charge there is. And then that C term, the capacitance, is really the proportionality constant of this expression. It's really that simple. The capacitor, depending on how close the plates are, how wide they are, what material is in here in terms of the dielectric constant, modulates how hard it's going to be, so what exact voltage you'll get for a certain exact amount of charge.
Makes sense, and I guess that's why when it's a bigger plate, it's easier for me to cram more charge on it for a given voltage.
Exactly, that goes back to the last slide we were saying. Okay, so the other analogy that I think Vivek's going to do is really thinking about this from the perspective of water.
Okay, so it's often convenient to think about capacitors with an analogy of water. It's not a perfect analogy, but it tends to be a pretty nice analogy to work with. Okay, so let's think about a tank of water, and we're going to pump water into the tank from the bottom. Okay, so we take this, initially this tank is empty, and when we start pumping water in, it's really easy, right? Because the tank is completely empty. So there's nothing fighting you when you're trying to pump water in. So water goes in nicely. However, as we start filling up the tank, if we're trying to pump water in from the bottom, now not only do we have to pump it in, but we have to push up the level of the water in this tank that's already full of water. So all the gravity forces acting on the water above the tank that's essentially full are now fighting, and you have to fight that.
Yeah, so each new bit of water has to push up against the bits of water that are already there. So
exactly,
the weight
that's
of
right.
The other water. Okay.
That's exactly right. And so it's sort of analogous here. Okay, so in terms of a capacitor, charging it, as the more you charge a capacitor, the harder it is to charge even further. Now we can also relate this to capacitance in terms of the sizing. So think about that. If you had a smaller tank, for the same amount of water will fill the tank higher. And by smaller tank, I'm referring to the cross-sectional area. If I have a tank that's say 1 meter square in cross-sectional area, and I fill it with 10 gallons of water, it'll rise to a certain level. If I had a larger tank with 10 gallons of water, it would not be as heavily loaded. What this says is for that larger tank, it's easier to fill, therefore, because there's effectively more space and you're fighting the liquid column less for the same amount of total water. So the same is true in terms of capacitance. Now, we can take this analogy in one final step further, and that is the following. So let's say I've charged that capacitor up. In other words, I filled the tank. Do you think that stores energy, Michel?
Sure. In the case of water, it's storing energy against the gravitational field, so there's a potential energy that water has. My guess is that once you store energy in a capacitor and you've got the electric field set up and so on, you could then release that energy through, say, a resistor in the same way as you could release the water stored in a big tank through some plumbing.
Right. So you could, if you had water stored in a big tank, as you released it, it could spin a wheel, for example. Similarly, in a capacitor, you can always recover the energy by emptying the capacitor. So you see how this analogy with water works. Now, at this point, we've talked about the analogous formalism of capacitor, and we've talked about the basics of capacitance. Michel, maybe you can talk about some real capacitor structures.
Yeah, let's do that before we get into some more equations. So there's lots of different ways that people practically make capacitors, and I thought I'd touch on a couple of different configurations just to give you some intuition. So one very common type of capacitor is what's called a coaxial capacitor. And here, instead of having two plates that are the same size facing each other, you have an internal conductor, and it's surrounded or sheathed by some dielectric. It could be air, it could be some material that's not a conductor, an insulator. And then outside of that, there's a cylindrical conductor that forms the outside. So the two plates are the inner metal and then the outer one, and the dielectric is in between. You see it's cylindrically symmetric. So there's a very common example of this that we see in everyday life. Vivek, do you know what that one is? Can you guess?
Well, of course, we deal with this in cables all the time.
That's right. So we see this a lot in lots of cables, in TVs and even sometimes in audio systems. There are various advantages to this type of setup that go beyond its use as, say, just a capacitor. But for the moment, it's just easy to think about just the capacitance part of it. Now, capacitors are often, here's an example of a mica capacitor, but really this what I'm about to talk about extends to many different materials. Very often what you do is you build these composites that are stacks of laminated stacks of metal, then insulator, then metal, then insulator, then metal, then insulator, and the alternating metals are sort of shorted together so that they form one giant terminal.
So this just looks like a bunch of parallel plate capacitors connected in parallel, effectively.
That's exactly what they are. They're sort of interdigitated with each other, and they're shorted so that they alternate.
By the way, historical note, the reason people used to use mica as the predominant material for these capacitors is mica is kind of an interesting material in that it's an insulator that you can peel off in really thin layers that are very mechanically robust. So people would take mica and sort of sheet it off into little thin layers and then put foil on each side to form these capacitors.
That's cool. I honestly didn't know that. So the same idea can apply to things that are flexible. And so again, another common thing you can do to generate something with a pretty high capacitance is you do this kind of alternating thing, but you do it with foils that are flexible, and you roll the whole thing up and you get kind of a cylinder version of this thing. There's other things you can do. So the one thing that I'm sure were taught in physics, but it's good to emphasize here, is that really any two conductors in the universe have a capacitance associated between them. And so, in these cases, we're purposefully trying to stack them real close to each other and have the overlap area really match. But you can have, for example, this piece of metal here that's flat, surrounded by a flat donut, and there'll be a capacitor where the electric field kind of arcs from one to the other. And here's a kind of a cross-sectional example where you see that there's one metal piece here and another metal piece here, and these two form the terminals to the capacitor.
And of course, as Michel pointed out, you can calculate this capacitance between two plates that are side by side. While in theory there's of course a capacitance that extends between any two objects, in the reality we deal with this only for objects that are relatively close to each other.
Yeah, that's right. And what's a really cool side point here is that many types of older touch screens that were capacitive relied on this idea, because if your finger comes down and rests somewhere between these two, it'll change the capacitance. And so if you're constantly monitoring that, you can detect when a finger is near. That's right. Not exactly how it's done in modern smartphones, but it's sort of a predecessor idea to the modern way to do it.
That's right. Okay. So now I think we've provided a good introduction to capacitors as a whole. Let's move on to actually doing some of the math associated therewith. So the first thing to talk about is the energy stored in a capacitor. Now, Michel already told you that there's a relationship between the charge in a capacitor and the work done to store it there. We know that it takes work to add charge to a capacitor. Given that it takes work to add charge to a capacitor, you know that the increment of work is, of course, a change in energy in that capacitor. So we can write that then as dE, the incremental amount of work done to move a charge onto the capacitor, as the voltage already on the capacitor and the increment in charge that is added. So this makes sense if you think about it. If I've got a voltage on a capacitor and I try to add in another charge, it's harder to do the more voltage I have.
Right.
So the more voltage I have on the capacitor, the more energy it takes to add an additional increment of charge. So this equation makes sense. So what we have then is dE is equal to V times dQ, where V is the potential energy of the capacitor, the voltage on the capacitor, and Q is the increment of charge, and E is the increment of energy. Now, we've already got a relationship between Q, V, and C. You remember from our previous section that the charge on a capacitor Q is equal to the capacitance times the voltage in the capacitor. Therefore, writing this in differential form, we can write dQ is equal to C times dV. So then we can take this equation and we can substitute into the top equation over here, and we get dE, the incremental change in energy, is equal to C times dV times dQ.
I foresee you are about to integrate to get the total energy in a capacitor.
You have great insight. Maybe it's because you've seen these slides before. So anyway, let's proceed and put this together. So what we do is we've got a differential form. We can integrate this. So if we integrate the right-hand side, we'll get an integral with respect to dV. If we integrate the left-hand side, we should get energy. And sure enough, so we'll then write the energy is equal to the integral from 0 to V0, whatever voltage we stop at, of CV dV. So C is independent of voltage, but that's the capacitance. It's a fixed parameter for the system, so we can move it outside. And what we're left with is a first-order integral of voltage, of a linear term. So you know that the first-order integral of a linear term is just the square of the term divided by 2. So we're going to get the energy is equal to CV square over 2, and the bounds are from 0 to V0. So if we were starting at 0, there's no voltage, which means we now have an equation for the energy stored on a capacitor. If we had a capacitor that started out in the discharge state, 0, and then we charged it up to some voltage V0, the energy stored in that capacitor is going to be half CV0 square. And this energy is exactly analogous to that water tank energy that we talked about earlier, because we can pull it out and use it to do things earlier.
Okay, that makes sense to me. So let's talk a little bit about capacitor current. Just to give you, again, a little bit of intuition. So a steady DC current into a capacitor, by now you should see that it means that you're going to get a linear increase in voltage, okay? Or a ramp, a linear ramp, I should say, because you could have a negative DC current and you'd have a negative ramp in voltage. In theory, this would keep going forever, but in practice, what's going to happen is if you have sufficiently high voltage across a sufficiently small gap, you'll exceed the dielectric breakdown of the material, the insulator, and you'll get arcing. This essentially is sparking or lightning. Basically, your E field is so high that you can the electrons can start jumping through the insulator. Okay? And of course, this would short it out. Now, the other thing I want to give you a little intuition about is AC current. So that's fine for a DC current, but now think about a current that's constantly and sinusoidally going up and down, right? It's a sinusoid, so it's going to be, the current will be increasing, and then it'll go down, cross 0, and go negative, and then come back up, and so on. It's a sinusoid. So since a steady positive current increases the voltage, you might imagine a steady negative current does the opposite. So if we pass a time-varying current that's always flipping polarity, positive and negative, you would assume that the voltage across the capacitor would do the same thing, right? And so for a fixed current, we can definitely infer the voltage. We want to leave it up to you. We're going to definitely come back to this and work this out for you, but it's a good exercise at this point before we do it more formally to think about what would happen to the voltage if the current was a sine wave. What do you think the voltage is going to look like? It's a nice little intuitive jump.
And we will look at that in the future, but now's a good time to stop. So we're going to stop this section now, and we'll pick up on more details of capacitors in a little while. See you next time.
See ya.